careful about that. I would not do. Oh, okay, we ready? Don't want to give my little theories here on how you treat people nicely. We're moving right into lecture 8. At the end of lecture 7, we had a malfunction, probably me, showing the answers to WebAssign. So there's an extra little video 7B, which shows you how to go to the past due assignments and click on the videos where I work out the WebAssign questions that are past due. Those are good places to go when you're reviewing for your final exam also, of course, before your test. But anyway, go there and see how to do it. If one of those videos does not work, you just need to send an email and we'll contact WebAssign and say, hey, there's a little problem there. All right, we're going to start with Test 2 material. We should have started this last time, but I wanted to make sure we had a good review. It's very important. Test 1, you make a good grade because the course just builds on itself. Got to be good at those derivatives. We're going to begin Test 2 material today. We've been looking at the derivative as slope of the curve, slope of the tangent line to the curve. And we've already had some insight when we had profit and marginal profit, cost and marginal cost. We've already really discussed a little bit of this, but we're just going to look at a couple other things that we can talk about as rates of change. A rate of change, a rise over a run, how something is changing when you're at some point. I guess I should go the other way. I keep forgetting. Rise over run, that's a slope. So a derivative as a rate of change. We don't just have to have changes in y's over change in x. We might have change in height over change in time, change in speed, velocity, change in distance over change in time. What's that called? Change in distance, velocity. Did I already say it? Yeah. Okay, see, I told you my brain works about a half a minute ahead of what my voice says. All right, so we're going to look at derivatives as rate of change. Again, that's just a slope deal. And then we're going to move on into 2.1 and 2.2, describing graphs using words and derivatives. And Sean, what you doing back there?
Turn off my phone.
Do what?
Turn off my phone.
Thank you. Thank you. Everybody be sure you turn off your phone. Thank you for prompting me to tell everybody that because we don't want the phone going off during class. All right. And then we're going to move into 2.1 and 2.2. We're now going to start to apply the derivative. We're going to use words, and then we're going to use the symbols of the derivative, which is leading us into curve sketching, because we want to get to those word problems, and if we can analyze the function, then we understand maximum and minimum values, maximizing volume, minimizing surface area, what price to pay at a movie so that you get your maximum money coming in or your maximum profit. I mean, they can keep raising the price of tickets at a movie, but there gets to be a place where some of us are not going to go. I think it's maxed out already for me. But anyway, you know, they have to, maybe they would like fewer people raise the price. Is that going to give them a maximum profit, or are they better off to sell the tickets cheaper and fill up the whole movie theater? You know, so that's where we're headed with all this. All right, let's start in on Test 2 material 1.8, derivatives as a rate of change. And if you'll also have your textbook out, because we're going to work some problems directly from the textbook in just a minute. Okay, 1.8, derivatives as a rate of change. Okay, and what I like to do when I start out with this is do something we can all relate to if you live in Raleigh and you'd like to go down to the beach. Okay, so along this axis, I'm going to put time in hours. And along the y-axis, I'm going to put distance. Okay, and this is going to be distance from our starting place, like from home, from NC State. And we're going to head down to Wrightsville Beach, or one of those wonderful beaches. And along here I'll put 25 miles, 50. Remember, your units need to be consistent. 100 miles. How far is it to the beach from here?
120 miles.
150. How far?
120.
Okay, we might head on down to Myrtle Beach. 150. All right, so we'll just do something like this. Hours. 1, 2, oops, let's make them a half. 1, 1.5, which is 1.5. 2, 2.5, 3, 3.5. I know when I was going down to Myrtle Beach, if everybody would stay off the highway, I could make it in 3.5 hours. Get out of my way. Here I come. Actually, that was more like 100 and, oops, it should be 125, so I'm consistent. Is that what you were going to correct me on?
Yeah, and then it should be 75.
What?
50, 75.
Yeah.
Well, I was too excited about the beach. We're just going to rip that out. Let's try again. Thank you. Thank you. I was thinking about how much I'd love to be there.
Going to the beach.
I'd like to, but I'm not. I'm going to stay here because I want to be with you guys.
Oh, yeah.
All right. 7 halves. All right, so we have 25. Can't multitask, can I? 75, keep me straight. 100, 125, thank you. 150. Y'all are just hoping I'm going to mess up, but I'm not. How'd I do? Yay, with a little help. Miles. Okay. All right, so we're headed down to the beach, and this distance here in miles, in miles, we're starting from our starting position, so normally we're at 0, 0. We get out there, and at the end of the first half hour, we're at 50 miles because there's a lot of traffic in town. Takes me over a half hour to get here, and I don't even live but 11 miles away, 10 to 11. All right, so we get 50 miles. Ooh, wait, we're flying. Half hour, we're at 50 miles. Okay, so we started out on the interstate. All right, then let's say from a half hour to 3/2 hours, we only get another 25 miles, and that's probably because we stopped to eat or there was a little traffic jam out there. And at the end of 2 hours, we're just going to make this nice. We're in a hurry. We're at 150. All right, I'm not going to put too many points because you get the idea here. We have points 0, 0. We have 1/2, 50. We have 3/2, 75. And we have 2, 150. Okay? All right, none of these numbers your parents are going to be too happy about when they hear it. All right, so you're on a trip. First question is, let's pretend that you did go visit your parents, and they said, how long you been traveling? And you go, 2 hours, and they go, you drove 150 miles in 2 hours, and they go, okay, I'm really looking at the slope of the line through these 2 points, slope of the line through these 2 points. The slope would be the difference in the distances, 150 minus 0, and let's put the units, that's miles. And the time is the difference in the x's, 2 minus 0, and that's hours. Miles per hour. That slope between those 2 points is going to give me what we call an average. Your book's going to call it an average rate of change, but in our case, it's going to be an average velocity. Average velocity, which is 150 divided by 2, or 75 miles per hour. So we're talking about an average rate of change. An average rate of change, in this case an average velocity because it happens to be hours and distance, is going to be the slope of what kind of line? Slope of the secant line. So when you're looking for something on the average, it is the slope of the secant line. Okay, and so in your exercises in 1.8, sometimes it'll ask you for the average of average speed, average growth, average whatever. Well, you're just going to get the 2 points. You'd have to have 2 points to get an average. It's going to be called average rate of change, average whatever. 2 points. All right, so I'm sure if that was your mom, she wouldn't be too happy about that, although she probably does it just as bad. All right, now we want to talk about what is called an instantaneous rate of change. Instantaneous rate of change. Instantaneous rate of change. Okay, the instantaneous rate of change if you're going down the highway is the moment you see the patrolman. Okay? At that very second, when you see the patrolman, what do?
Slam brakes, speed up.
Hit the brakes. What?
Slam brakes or speed up.
Slam brakes probably be a better idea, not speed up. Okay. You hit the brakes, but as you're hitting the brakes, what's your eye doing? Aren't you looking at the speedometer? Because you automatically think you're speeding, right? When you see the patrolman, don't your eyes glimpse down to see what your speed is? That is your instantaneous rate of change at that very second. All right, so we want to know, like, what is the speed at this very second? All right, so an instantaneous rate of change is at one point on your curve. All right, well, this 1 point, the way I drew it, looks like we're on cruise control going down the highway because, you know, your speed is not constant. But anyway, if we were on cruise control, let's see what that would be. So we're on cruise control where our speed does not change. So that would be the difference in the y's, 150 minus 75, over the difference in the x's, which is going to be 2 minus 1.5. So it looks like we will have 75 divided by half. Oh, man, we're in a race car, are we not? 75 divided by half, that would be 150 miles per hour. You better be hitting the brakes on that one. Okay, all right. Very unrealistic story here, I hope. But if you were on a cruise control and your car would go that fast, I don't even know if it will. You hear me? I don't know that my car will go over 80. Okay. All right. So, but the speed at a particular moment is your instantaneous rate of change, or what else would you call that? At a particular spot? Derivative. Derivative. Okay. So if you have a curve and you want to know what is the rate of change at that very moment. Now, when we're working as derivative as rate of change, we want to be careful to keep up with our units. Our units. Label what your units on the x-axis and y are, because when you do a change in y or a change in x, when you take your units with you, it will tell you what's going on there. When you hear miles per hour, you know you're talking about velocity. Okay? All right, so that is the big highlight of this section. So we're going to go to the book and just work a couple problems together. Okay, I'm on page 133. Page 133 in the book. And we're going to look at problem number 6, which is just going to refer to A, B, and C right here. Okay. Now, they labeled what the words are for each axis. So T represents the years after 1900. Can you see that? Good. All right, so if you looked at 30, that would represent what year, everybody? 1930, okay? All right, now along the y-axis, it says mean. That just means the average farm size. That would say the Americans had an average farm size in 1900 of, looks like about 150 acres. The average farmer had the average farm size of 150 acres. See how that works? Okay. All right. Now, question A, and you tell me how to do it. What was everybody say that word, average rate of growth in the mean farm size from 1920 to 1960? Whenever you're going to find the average of something, you need 2 points, and they're giving it to us. Very good. You are good, good, good. All right, so 1920, let's see if we can guess what that is. In 1920, it looks like there were 150. All righty. So we have 20, 150. We have to remember that this 20 represents 1920. All right, so 1960, that looks like 300, doesn't it? So we have 60, 300. Okay? All right, now we want the average rate of growth. Average rate, so I'll just do average, which is the slope of the secant line between those 2 points. And when I say 300 minus 150, what's my units up there going to be? 300 minus 150, what? Acres. Very good. And then we'll say 60 minus 20, and what's the units going to be? Years. So when I find the average rate of change, the answer is going to be acres per year. All right, so we have 150 over, is that 40? Okay, 150 divided by 40 is 3.75 acres per year. All right, now let's make an interpretive statement here. From the year 1920 to 1960, what?
Yeah, average rate of change.
But use it in terms of this.
You get 3.75 acres or more every year?
Yes. From the years 1920 to 1960, the average farm size went up 3.75 acres per year. Okay, see how you read it right off? All right, so if in 1920 you had 150 acres, how many acres would you sort of expect in 1921 the average person to have? 153.75. You guys are good, good, good. Okay? All right, let's go to part B. Part B says, how fast was the mean size, farm size rising on January 1st, 1950? I want to know exactly on the year 1950, January 1st, how fast was it growing right then? What am I needing to look at? Derivative. And when you hear derivative, you also think about slope of the curve, slope of the tangent line to the curve. Okay, so let's go back to our figure. You notice at 1950 they put in a tangent line for us. All right, let's see if we can guess what that slope is of the tangent line. You need to find some points you recognize. Sometimes it's kind of hard to see. Yeah, it looks like 1940 and 1980. So that's 50, 100, 150, 200. Is that 200 over 40? 150? 50, 100, 150. Whoops. Okay. The year 40, it's at 150. The year 80 looks like it is at 400. Okay, couldn't see it from my angle. All right, so we're looking at the slope of the tangent line, which at, wait, we're not at 40, we're at 50. At 1950, right here. And that looks like it's pretty close, but not exactly at, but it's close to 200. 50, 200. All right, it's a little off. It looks a little bit bigger than 200. Maybe 210? What do you think?
Yeah.
210? All right, looks like 210. So we have 400 minus 210 over 80 minus 50. What's the units in the top? Acres per year. So we have 400 minus 210. Should be able to do that in our head. 190 divided by, what, 30? And we get 6.333 is a third, right? Acres per year. All right, so the question is, how fast was the mean farm size rising on January 1st, 1950? And we had to get a little tangent line in there and estimate the slope of that tangent line, and it comes out that it was growing at about 6 1/3 acres per year. Is that good? All right. Question C. Was the mean farm size rising faster on January 1st, 1960 or on January 1st, 1980? Was the average farm size growing faster, rising faster in January 1st, 1960 or January 1st, 1980? What are you going to do to figure that out?
The slopes of it.
Look at the slopes there. Okay, let's see if we can sort of guess what the slope looks like. 1960, that looks like the slope is, look for that little line of best fit. Looks something like that. I'm right at 1960. Okay, 1980, remember that slope. 1980, the slope looks like it is about right here. Okay, so which one had the sharper slope? This one? 1960 looks more like that. So the average farm size was rising faster in 1960 than in 1980. Okay, everybody good? All right, let's go to problem number 10. Problem number 10. We have that liquid is pouring into a large vat. After T hours, somebody they paid came up with this formula that would tell you how many gallons of liquid are there. 5T minus the square root of T. All right? At what rate is the liquid flowing into the vat? And it tells you gallons per hour. At exactly T equal to 4. It's not asking you the average rate that it's pouring in. It wants to know exactly at that moment how fast is it pouring in. Okay? All right, let's set up a visual on this. Let's see. Might as well do it right here. It's fine. Okay, this is problem number 10. This is page 133 from section 1.8. What would I have along the x-axis here? Words.
Gallons.
T, which is in hours. Okay? All right, what would I have along the y-axis? Gallons. All right. And I don't know what the graph looks like, but I'm going to at least have some kind of little curve coming through here. And the question is, what is the rate at exactly T equal to 4? And it tells me already the units are gallons per hour. All right, so what are we going to do to this function? And let me give it a name. How much is poured in? Gallons. I'll just do a big G. Big G is equal to 5T minus the square root of T. How am I going to find the gallons per hour at this one point, everybody? Take the derivative and then evaluate at 4. Okay? So we'll take the derivative of G with respect to T. Let's rewrite this as 5T minus T to the 1/2. Okay. So the derivative of 5T is 5. And what's going to be the derivative of T to the 1/2? Okay, 1/2 T to the negative 1/2. So that's going to make us have a minus 1 over 2 square roots of T, right? Done that one enough that you can visualize it. Here's the negative. Brought the 1/2 down. Rewrote, decreased by 1, sent that to a negative 1/2, which I put in the denominator. Now we're going to evaluate at T equal to 4. Put it right here. So we have 5 minus 1 over 2 square roots of 4, which is 5 minus, square root of 4 is 2, 2 times 2 is 4, minus a fourth, and so I guess that would be 4 3/4 gallons per hour. Okay. So you can see it's not a straight line that describes how the liquid is poured into this vat. And so at the moment when T is 4, whatever the shape of that curve is, this little curve has a slope of 4 3/4, meaning over the next hour we would expect about 4 3/4 more gallons to enter. That's an approximation to it. It's not exact because we don't know what the curve looks like. All right, everybody good? Easy? Most people think this is hard. Okay, let's go to problem number 14 and just talk how we would do it. Page 134. Problem number 14. Okay. All right, we have a helicopter. It's rising straight up in the air. Its distance from the ground, t seconds after takeoff, is s of t equals t squared plus t. So s is how far the helicopter is off the ground. T is in seconds. S is in feet. All right, let's get a quick visual on this. You already know what the graph of s of t equals t squared plus t looks like, don't you? A little parabola. All right, so along this axis we have t seconds. Along this axis we have s feet. And when t is equal to 0, of course you're at 0. When t is equal to 1, it's a 2. You know the thing's going up anyway. All right, so there's kind of the graph of s of t. All right, so we have s of t equals t squared plus t. All right, the first question says, how long will it take? What are you going to be looking for? How long? Time. How long will it take the helicopter to rise 20 feet? So you're looking for time, and the height above the ground is 20 feet. What kind of formula are you going to put that in?
Solving for this would be very.
Yeah, it already says its distance from the ground is given by t squared plus t. How long, you're just going to solve that for t when the distance above the ground is 20 feet. So you'd have 20 equals t squared plus t. Right, you thought that was a trick question, didn't you? All right, how do you solve this? It's a quadratic equation.
In the 20 hours.
Okay, you got to get it equal to 0. Don't forget that. And this one is real good because it factors. T plus 5, t minus 4. So you got t at negative 5 and t at positive 4. How do you know which one's going to work? All right, we're talking about from liftoff. We know the parabola is going to swing back around, but we're only looking at t greater than or equal to 0 liftoff. So it would take 4 seconds for it to reach 20 feet. Does that make sense? Okay. Part B. Find the velocity. Everybody good? Was that too fast? Negative 5 can't work because that's negative time. Okay. Find the velocity, let's do that first, of the helicopter when it is 20 feet above the ground. Velocity you think of, in this case it would be
Straight. Speed.
feet per second, velocity. And if we have the distance function, how do you find velocity?
Derivative.
Take the derivative, right? ds dt, your units would be feet per second, so that would be your velocity, correct? So the velocity is 2t plus 1. Okay, let's go back to the question. Find the velocity when it's 20 feet above the ground. Well, when was it 20 feet above the ground? At 4 seconds. So we'll evaluate this at t equal to 4. So we get 8 plus 1, we get 9 what? What's the units? Feet per second. Okay, so 4 seconds after liftoff, it is rising at 9 feet per second. Okay? Velocity is 9 feet per second. Everybody good? All right. Now, I had another question on here. Acceleration. How do we find acceleration from velocity? How your velocity is changing. Isn't that when you mash on the gas? That's how your velocity is changing, right? You're accelerating. All right. That's the way I like to think of it. So if we take the derivative of the velocity, which means we're taking the derivative of the distance, so it's really a second derivative. All right. So the derivative of the velocity, which is going to give us 2. All right. Somebody needs to give me the units on this.
Feet per second squared.
Yes, the velocity was already feet per second divided by dt per second, which comes out to be 2 feet per second squared. So you're accelerating at 2 feet per second squared. Okay, very good. Velocity is feet per second, time is seconds, so feet per second, which is feet per second squared. Okay, 2 feet per second squared. Acceleration. All right, everybody good? All right, let's go to problem number 20. All right, the reason we're going to problem number 20 is because it looks worse than it is. Suppose f of 25 is 10. What is that giving you right there? A point. When x is 25, y is 10. It's giving you a point. And the derivative at 25 is negative 2. Well, if it were in distance, it would be velocity. Okay. All right. So we have the point 25, 10. 25, 10. We have a derivative at 25 to be negative 2, which we know is the slope of the curve there. So we don't know what the curve looks like, but the slope here is negative 2 at that particular point. The derivative at 25 is negative 2. And let's just estimate a couple of these. Let's do B. Based on that information, what would you say the point at the y value at 26 is? Okay, if you're at 2510 and the slope is negative 2, it's like you're coming down 2 over 1, right? Slope change in y over change in x. So you go down 2 over 1. So if you went over 1, that's 26. Down 2 would get you to 8. All right, what would be 24? So when you're at 24, what would the y value be? 12, because you would go over 1 this way and up 2. Okay, you had a negative slope anyway, so you go over 1, negative 1 this way, positive 2. 2 over negative 1 still gives you negative 2. All right, and then it asks you to find some other estimates. All right, now let's pretend we don't want to think and do anything. Maybe not, that's not the right word. Let's pretend we want to be efficient. If I know a point and slope, could I easily write an equation of a line? Yeah, so let's write the equation of the tangent line. Y minus the y coordinate equals the slope times x minus the x coordinate, or y equals negative 2 times x minus 25 plus 10, if I just solve that for y. All right, so I had a point, I had a slope, I did the point slope form. All right, so y is negative 2 times x minus 25 plus 10. So let's answer our same questions that we just did. When x is 26, y is equal to minus 2, 26 minus 25 plus 10. Negative 2 plus 10 is 8. Bingo, 8. When x is 24, y equals minus 2, 24 minus 25 plus 10. Negative 2 times negative 1 is positive 2. 2 plus 10 is 12. Bingo, that's what we saw visually. So for these particular problems in the exercises, you can put in a visual, understanding what the slope is, or you can just not have to work too hard and write the equation of the tangent line, and you're just estimating values using your tangent line. Is that clear, everybody? Easy, easy. The answer is yes. Okay, let's go to problem 28. Next page. All right. You've already had some experience in doing all of this. This book is really good to keep giving you flavors before you get to a section. F of t will be the value in dollars of one share of a company X days after the company went public. So a private company decides to go public, which means they're ready to start selling stock on the New York Stock Exchange or the NASDAQ or something, somewhere. All right, so make sure you know what the words are. Turn to your neighbor and tell them what f of 100 equals 16, and be sure you use units. If you will draw your little coordinate system, a lot of times that helps you with the words.
In 16 days, the value of one share of the company is
Everybody got it?
$100. In 16 days, that was one share.
Okay. What goes along the x-axis? Days after the company went public. Days after company goes public. Means they've been selling stocks for X days. Okay, what's along the y-axis? Dollars. What kind of dollars? Price of one share of company stock? Value in dollars. Okay, this is dollars, which is really the price of the stock. Does that make sense, everybody? Okay, so the first thing they give us is f at 100 equals 16. So I have what point? 116. I make a big deal on this because I can't tell you how many people miss this on test. If it's f of 100, the 100 goes with the x, is 16. That's the value of the function. So the 100s. Okay, second row. Somebody translate 116 for me, this point.
After 100 days, it made $16. The price of the stock, $16.
Okay, so you leave out the word made. I heard you say it made $16. Okay, the price of the stock is $16 100 days after it goes public. Okay, it's not made. We don't know how much the stock started out with. Okay, good. Very good. Everybody good? Okay, the next thing it tells us is the derivative at 100 is 0.25. The derivative, f prime of 100, is 0.25. Look at your units that go with the derivative and tell your neighbor what the 0.25 means.
The days after the 100th day, the price increased. Price increased.
Okay, so it's going to be the change in your y, which is going to be money, right? And what's in the denominator? Days. And you could put this like 1 day.
Quarter a day.
Okay. All right, so you're going to translate f prime of 100 to say third row. Somebody tell me exactly what that means. Third row. Let's keep y'all awake back here. Tell me.
That's the amount of like increase per day.
When?
After the 100 days.
On the 100.
On the 100 days.
Okay. Okay, so when you are on the 100th day, the price of the stock is going up 25 cents per day. If you get too far away from the 100th day, you're probably on some kind of error. So it's not every day after that. It just means when you're on the 100th day, the price of the stock really went up that 25 cents that day. Okay? All right. Everybody got it? 25 cents per 1 day when you are at the 100th day. Because a lot of times when stock comes out, they've already got these people buying it, so they'll start it here. It goes way up real fast. Probably should have done it the other way. It goes up real fast, looks like this, and then it maybe starts to level off by the time you get out here. Okay, so it's going up 25 cents a day when you're about 100 days out, but that may not continue. All right, now the next question says, let me give you the words and you tell me what the symbols are asking you. Estimate the value of one share on the 101st day since the company went public. what would you estimate the value of one share to be on the 101st day? Yes, you guys are too good, too good. So at 100, it's $16. We're expecting it to go up about 25 cents per day. So we would approximate on the 101st day it to be $16.25. Okay? Easy, easy. That's because you guys are good. Alrighty. You have fun. You got lots of problems to work here. The idea is that the derivative is not just about changing y over changing x, but whatever your functions are, look what your x-axis represents, your independent variable, your y-axis, and a derivative is changing y's over changing x. Instantaneous at the moment versus average slope of a secant line. All right, we are moving into Chapter 2 now. Chapter 2. And I actually like to do Chapter 2, Section 1 and 2 together. So Chapter 2, Sections 1 and 2. And what we're doing is describing graphs with words and using derivatives. All right? And Chapter 2, Section 1, we've already used the words in pre-calculus as well as difference equations. So we're doing good. All right, I'd like for everybody on your paper to show me an example of two functions that increase. Functions that increase. All right, two different graphs of functions increasing. Or you could do 3. Or you could do more. Okay, will you just hand me your paper? All right. So as you move from left to right, the y values are getting bigger. That's when that increases. As you move from right to left, left to right, the y values get bigger, so that increases. Another one that increases, anybody got a picture that's different? Yes. We could also have a straight line going up. That's a function that increases. Okay? All right, now, when we're talking about the slope of a curve at a point, if I took a slope right here, or slope right here, slope of the curve, slope of the tangent line to the curve, what would you say, what kind of slopes you would have to all these three curves? Positive slopes. And what symbols do we represent when we're talking about a slope that is positive? Or slope of a curve. Okay, slope of a curve, you think derivative. And if the slope is going up, yes, thank you, positive derivative. So when you have a function that increases at a point, you're going to have a derivative which has to be positive, a derivative that is positive. Okay? All right, so anytime you have a function increase, which means it's got to go up somehow, that is going to be a derivative that is positive. All right, now draw me some functions that decrease. Functions that decrease. Okay. All right, here's 3 pictures of functions that decrease. As you move from left to right, the y values are getting smaller, and that's kind of a straight line there. These are, the y values are getting smaller here, so that's decreasing. The y values are getting smaller here, it's decreasing. Okay, everybody see those? All right, if I pick a point on these curves, what kind of slope do you have here? Negative slopes. And how are we going to translate that? Derivative is negative. Okay, so when we know the function decrease, it just means it goes down somehow, negative slopes, and the derivative will be less than 0. Okay. What about if we say the slope of the function increases? Okay, draw a picture that has the slope of the function increasing. The slopes of the functions are increasing. Okay, so what's that picture going to look like?
Straight line.
Any increasing function?
That would be, the slopes wouldn't be increasing because they're constant on a straight line. Right, if you got a straight line, the slope is a constant, so your slope couldn't be increasing. Draw your picture where your slopes just keep getting bigger and bigger and bigger. The slope of the curves get bigger and bigger. Who's got one for me?
Not me.
All right, hand me yours and let's investigate it. I mean, you're just guessing. Nobody's... All right, so if the slope of the function increases, look at the slope right here. And then look at the slope right here. Did the slope get bigger? No, the slope actually decreased here. This is a slope of the function decreases. All right, so try again. Slope of the function increases. Let's see what you have. All right, let's see if this one works. Here's a point here. Here's a point here. Did the slope of the curve get bigger? That's an increasing slope. Check. I need another one. Somebody got one that's drawn a little different? Anybody got another one? Try that the function decreases but make the slopes increase. Try a decreasing function but make the slopes increase. Okay, let's see if this one's it. All right, is the slope right here less than the slope, say, down here? That's a very negative slope. This one is less negative, so therefore the slope is increasing. All right, so when you're looking at the slope increasing, we have a name for this. It's called concave up. Concave up. So you're really looking at the derivative of the derivative. Because if the function, if you got a function here that is increasing, function increasing, that's a derivative. And then the slope of an increasing function, slope of an increasing, that's a derivative of a derivative. So this is a second derivative greater than 0. All right, when you're looking for the slopes increasing, and another way to think of this is slopes. Well, the slope is, we already have a slope, and then we're going to take the slope of the slope, and you want it to increase, so you have a second derivative. Slope of the slopes. You're doing how are the slopes changing? Changing the slopes. A derivative is a change in the slopes. All right. So anytime you have a second derivative greater than 0 on your function, your slopes are increasing, and that will be concave up. And what happens with concave up is your little tangent lines are below. It's like it holds up the function. Your little tangent lines to the curve are beneath. And one easy way to remember this is silly, but it helps. Second derivative that's positive, you got a little concave up. Okay? All right. So slopes of functions that increases, you could watch this very carefully. It's not the function that's increasing, it's the slope that increases. So start out this way. I could always have functions that increase or functions that decrease. I'm interested in the slope of these two increasing. So the slopes have got to get bigger. So you come around this and sketch it so that it goes like this. There's a little concave up. Or if you have one like this, you just sketch over it to look like that. Those slopes are increasing because that's very negative to less negative. So this has a first derivative greater than 0 and a second derivative greater than 0 because it's concave up. This one has a first derivative less than 0 because it's the function decreases, but the second derivative is greater than 0. All right, so a function that where the slope increases, you will have second derivatives greater than 0. Okay? All right, now we want to look at slopes decreasing. Slopes. I need this all on the same page. Let me see if I can slide this. Slope of the function decreases. So slope decreases. All right, let's get a picture off second row. Slopes decrease. That's increasing. That slope is increasing there. That's a decreasing slope. Oh, well, yeah, I guess that is always decreasing. You're right, you're right, you're right. I'll take yours. I wasn't expecting that, but that's perfect. You're fine. Good. Let's see what you got. Okay, can I take yours? All right. The slopes are decreasing. Let's look at these. All right, decreasing slopes. Let's see. If I have a point here and a point here, are the slopes getting smaller? I'd say yes. If I have a point here and a point here, would I say the slopes are getting smaller? Yes. So this happens to be where the function increases. That's a first derivative greater than 0. But slopes decreasing is a second derivative negative. This happens to be one where the first derivative is negative. Why was that first derivative negative here? The function decreases. And then second derivative is also negative. All right, here's the way to remember it. Second derivative negative, concave down. Second derivative negative, concave down. All right, I had one more picture here which was absolutely perfect, caught me off guard. This is an example of a function where it increases till it gets here, then it decreases, but it is always slopes decreasing. If you go from here to here, this slope is more positive than this. What kind of slope do I have up here at the top? 0 slope, because it's not increasing or decreasing at the vertex. So how would you use that with symbols? What would be true about the tangent line to the curve at the vertex here? A horizontal tangent line? 0 slope. It has a 0 slope. So at the vertex, it's neither increasing nor decreasing. Okay, and then over here, this is a negative slope, but this one is more negative. So that's another good example of a second derivative, which is always less than 0 because it's always concave down. On this side right here, you have a first derivative, which is, what kind of derivatives over here? First derivative. Positive. And on this side, what about your first derivative? Negative. And then at the top is where you have a horizontal tangent line, and the first derivative is 0. Okay? Is that good, everybody? So second derivative less than 0, that's going to be your concave down. And what happens with concave down is your little tangent lines are on top of the curve, like pushing it down. All right, now, we know when we have a parabola, we have a maximum point or a minimum point at the vertex. This is called the first derivative test. Wherever your curve goes from increasing to decreasing, you have an extreme point. If your curve goes from increasing to decreasing, right up here at the top has to be an extreme point. Or if it goes from decreasing to increasing, you have to have a minimum point. That's called the first derivative test, using your first derivatives to locate extreme points. All right. Are we good, everybody? Would you pass those back? Thank you very much for sharing your work. All right, slopes that decrease, that's where you're going to have your second derivative less than 0. All right, let me turn through the pages in section 2.1 and see if I got all the words. We'll turn through the exercises, the pages. Page 142. Page 142. We know that functions increase on an interval as you move from left to right whenever the previous y value is less than the next y value. So really we say when we move from left to right, that's not your left to right, is it? When I move from left to right here, left to right, the y values are getting bigger. On an interval, it's increasing. Decreasing, when you move on an interval and the y values get smaller. We already know that. Okay, relative maximum and minimum. A relative max or min is a point in which the graph changes from increasing to decreasing. That would be a relative max. And when it changes from decreasing to increasing, that's called a relative min. Now, relative, this is the way I remember relative. In order to have a relative min, you've got to go from decreasing to increasing. So you've got to have points around it, like your relatives. They've got to be all around you, your little neighborhood. All right, so if you're going to have a relative max or min point, you have to have the curve on both sides of that point because you've got to go from decreasing to increasing or increasing to decreasing. Okay? Now the next part is absolute max or min. If you have a restricted domain, you may not have points on either side of something. And let me see if I can draw this so we can illustrate the difference between absolute max and mins and relative. All I do is remember that relatives means I have to have friendly points all around it. Okay? And absolute means go and find the absolute biggest or the smallest. Okay? Doesn't matter if they have friends around, relatives. All right, let me see if I can just draw a figure that will illustrate this. Okay, this is some kind of weird function that has a restricted domain. All right, and let me just label some points here best I can. So this would be A corresponding here, B is up here, C, D, and E. Okay. The question I'm going to ask is it a relative max and min? Is it an absolute max and min? Well, let's just take care of the absolute max and mins first. Do you see the absolute maximum point here? D. Okay, this is an absolute max. It is the highest point on my curve. Okay, based on my restricted domain. Do you see the lowest point, the absolute lowest point? A. This is the absolute min. Now, often when you read problems that says find the maximum or the minimum, the means the absolute. You don't usually see that word in there all the time. All right. Now we want to go to what are called relative extreme points, relative max, relative mins. Okay, could A be called a relative min? For it to be a relative min, it has to go from decreasing to increasing. What's wrong with A being called a relative min? It doesn't have any family around it. You have to be all around it. It would have to have come in this way and then gone up. Okay? So this absolute min is an absolute minimum point, but it's not also a relative. All right. Would you say B is a relative max or min? It's a relative max because if you just get all around little b, this is the high person here. This is the king, all right, but he's just surrounded by his little relatives, so he's the maximum point. Everybody got it? But it's not an absolute. It's just relative. All right, C. What would we call C? Relative min. Couldn't be the absolute because it's not the smallest point. All right, now could we call D a relative max? Yeah, it's still called a relative max because it has points all around it and it is the highest point in its little neighborhood, in its little family. All right, now what would we call E? Nothing, exactly. It's an endpoint of a restricted domain. It's not a relative min. It's not an absolute min. It's just where the endpoint ended, the graph ended. Everybody good? Okay, very good, very good. All right, let's see what else is in here. Page 146, concavity. Is concave up at a point on an open interval if the tangent line lies, is concave up if the tangent line is underneath it holding it up. Is concave down if the tangent line is on top pushing it down. That's basically what this graph, this information on page 146 says. Okay, inflection point is terminology. An inflection point is the point on the graph at which, of course it has to be a continuous function, in which the graph changes from concave up to concave down or down to up. No, not usually. No. I have to be very careful answering yes and no questions. He wanted to know if an inflection point is where you have a relative max or min. No, it's the point where the concavity changes. So if your graph goes from concave up and then switches to concave down, I want you to tell me what happens to the tangent line here. This is concave up, so the tangent lines are underneath. When it's concave down, the tangent lines are on top. What happens at the point where the concavity changes?
Slope is zero.
No, the slope is zero up here where you have horizontal tangent lines. Let me just, where would I draw the tangent line here? Does it go underneath or on top?
On top.
Goes through. Because if you're going from underneath to going on top, then this is going to be the inflection point is where the tangent line actually crosses, not vertically, I drew it that way, where your tangent line crosses through the graph. Okay, you got a tangent line underneath holding it up for concave up. Then when you get to that point, the tangent line's got to go through the curve to start coming down on it. So an inflection point is really going to be where your tangent line crosses through your graph. Okay? Alrighty. Let's see if we can answer some questions here. This is in page 149, 2.1. Alright, 2.1 was using words. 2.2 is using the symbol, so we'll put it all together here. Alright, part 1. Which functions, all these little pictures here, are functions that are always, the function is always increasing. So tell your neighbor, the function always increases. Function always increases. The function increases. The function itself increases. Okay, what is it? A, E, F. I think you're right. The function increases just means the y values get bigger. So in A, as you move from left to right, the y values get bigger. E, as you move from left to right, the y value gets bigger, and it showed this little horizontal tangent line here to let you know it's just going to get closer and closer to that horizontal tangent line, but the y values are getting bigger. And F, the y values are always getting bigger. So what would you say about the first derivative for A, E, and F? How do you represent the function increases? First derivative is greater than 0. Correct. All right, part 2. Which functions are always decreasing? The function decreases always. C, D, anything else? That's it. Okay? All right, number 3. What's the difference in the question to number 3? What's increasing here? Slope increases. First question was function increasing. Now we're looking for increasing slopes. What's the visual on the increasing slopes? Concave up or down? Concave up. So which of these graphs are always concave up? That's A is a concave down. B.
D.
C is a concave up. D is a concave up. I think that's it, isn't it? Concave up. Some people like to think of it with sort of hold water. Sort of hold water a little bit, but really it's your tangent lines are all underneath holding it. If you try drawing little tangent lines. So the slopes are increasing at B, C, and D. What kind of derivative? What's the rule for the derivative if it's concave up? Second derivative is positive. Happy face. All right, question number 4. The slope decreases. Slope always decreases. A and E. Okay. Decreasing slopes, if you just kind of look at the slopes, they're getting smaller. It's really a concave down. It's like if you put a little drop of water there, it definitely falls out. So A and E, I think, are the ones that are always slopes decreasing, and that's a second derivative negative. Everybody got it? All right, was there anything else in here? I think I'm going to skip that and let's go to 2.2. 2.2. I'm on page 154. All right, this is the first derivative rule. And this happens to be at a particular point. We've been looking at in general. But if you wanted to know when x is exactly equal to a, if your derivative is positive there, it's going to tell you you have a curve, a function that increases there. Whenever your derivative at a particular point is negative, the function is going to be decreasing there. That makes sense, doesn't it? Okay. That's at a point A. We've been talking about overall. All right, page 155, the second derivative rule. Okay, as soon as you saw second derivative, what are you thinking about visually? Second derivative. Concavity, right? So when you have a second derivative greater than 0, you're thinking concave how? Up or down? Second derivative. Up. Second derivative is a little happy face. Okay, second derivative at a point A, positive, it means it's concave up there. Second derivative negative is going to mean at that point it's concave down there. Okay, we're going to have fun shortly, in case you're not having it already. All right, page 158, the exercises. I picked out a lot on here because this is kind of the meat of where we were going. 2.1 was just the words. Now 2.2 is symbols. All right. I have some pictures over here that I'm going to put on the screen in a minute, but we're looking for functions that have a positive first derivative. Okay, give me a visual in words. What does it mean when the first derivative is positive? The first derivative tells you slope. Is the slope positive? So it just tells you what kind of function? Increasing function. 2 says when the function has a negative first derivative. So you're looking for functions that decrease. Part 3, once we get to the pictures, I'll say these words again. We're going to look for all functions that are always have a positive second derivative. What is that going to be? One that looks like what? Concave up. Negative second derivative? Concave down. All right, I'm going to put the pictures on the screen and we'll go through them. Okay, this is at the top of page 159. All right, we're looking for functions that are always, that will always have positive first derivatives. Does this one always have positive first derivatives? No, because what kind of derivative is right here? First derivative is negative here because it's decreasing. What about this one? Is this positive first derivatives? No, because that's decreasing. All right, is this positive first derivatives? No. That's negative, negative, negative. They're all negatives. All right, what about this one? No, not always. Okay, what about E? Does it have positive first derivatives? Yes, so that's an increasing function. What about this one? No. Okay, so the question was, is it positive first derivative for all x? See, this is a positive first derivative in here, but it said for all x. Everybody got the words? Okay, which functions have negative first derivatives for all x? B, because it's always a decreasing function. What about C? It looks pretty always decreasing. And F. All right, now the next one, 3, is positive second derivative. You're thinking positive second derivative? Always concave up. Is this one always concave up? Yes. Is this one always concave up? Yes. What about this one? No. Nope. What about this one?
Yes.
Yes. How about E? Yes. And F? No. Okay. All right. Positive second derivative, your brain is thinking always concave down. That's a concave up, concave up. Is this one always concave? No. What point, what do you call that? Yeah, a little inflection point right there where the concavity went from down to up. Right in here is your inflection point. All right, is this one second derivative positive? Second, oh, I meant negative. I'm sorry. It was second derivative positive. So that's not the answer to 4. Is this one second derivative negative? How about this one? Yes, very good. All right, let's go to problem number 10. This time they're going to want you to sketch a graph based on this little bit of information they're going to give you right here. By the way, wherever your first derivative equals 0, remember you have that horizontal tangent line there? That is a possible extreme point. But it's not always. I need to write that down and make sure that's very clear. I forgot to tell you that piece of information. First derivative equal to 0. Put this in big letters. Possible. Possible extreme point. Possible extreme point. Okay? So here's my examples. If I have a curve that looks like this, that would be, I have a first derivative right here equal to 0, and it's a minimum point. I might have a curve that looks like this, and it's vertex. So this is an extreme, this is an extreme. But the graph of y equals x cubed at 0 looks like this, and it looks like this. Y equals x cubed. At the point 0, 0, if I take the first derivative, which would be 3x squared, evaluated x equal to 0, the derivative right here at 0, 0 is 0. But looking at it, is that an extreme point? No, because it went from increasing to increasing on both sides of it. And the first derivative test says you're not going to have an extreme point unless you go from decreasing to increasing or increasing to decreasing. This went from increasing to increasing. So this is not extreme, even though the first derivative was equal to 0. So the key word is where we have a first derivative equal to 0, it is a possible extreme point. You don't know until you check for increasing to decreasing or decreasing to increasing around it. Okay? All right, one more important piece of information. Concavity. If we're looking for a concavity change, the inflection point. All right, so we're looking about a second derivative equal to 0. And the key thing here is this is a possible inflection point. Possible inflection point. I'm going to give you an illustration. All right, if your curve goes from concave up to concave down, this is the inflection point. The definition of inflection point is where the concavity changes. So this is a second derivative over here that is positive. This part is a second derivative that is negative. And if it changes from positive to negative, the inflection point by definition is where your second derivative equals 0. All right, now, why do you have to check concavity? Well, here's my counter example. If we take the function y equals x squared, we know the graph looks like this. Okay. If I take at 0, 0, if I take my first derivative and evaluate at x equal to 0, it is 0. So this is a possible extreme point. You know your first derivative when you're less than 0 is negative. First derivative greater than 0 is positive. So it is an extreme point. But if you go to your second derivative, second derivative, shoot, that didn't equal 0. I meant for it to. Second derivative here is 2. And 2 is always greater than 0. It just tells you your entire graph is concave up all the time. All right, where's my example? Okay, wrong example. I was trying to find one where second derivative is equal to 0. That one didn't work. But wasn't that a good problem anyway? Yes, yes, yes. All right, let's try another example. I'm looking for my counter example. Here's one for sure. Y is equal to x. Looks like this. All right, and we want to know, is there an inflection point? And the answer is no, because there isn't any concavity at all anyway. But if you didn't know what the picture looked like, when you do your first derivative, you get a 1. First derivative is 1, which tells you your curve always increases. All right, when you do a second derivative, the derivative of 1 is 0, derivative constant 0. So you think, well, there might be an inflection point on here, say at x equal to 0. But because there is no concavity changes at x equal to 0, there is no inflection point. Just because the second derivative is equal to 0, there's still not an inflection point there. Inflation has got to be where the concavity changes. Okay? All right, y'all don't seem overly impressed with that. All right, let's go to problem number 10. Okay, page 158. You're going to make a sketch of this graph based on this information. So use words with each of the symbols. Use words with each of the symbols, and you'll know how to sketch the graph. And because we're about to run out of time, we're going to do this one together. All right, everybody see it? All right, I'll show you my work after I do it, but you're going to help me translate the words as we go. All right, when you see -2, -1, your brain said, hey, I have a point. So just write down that that's a point. And then you have 2, 5, and that also is a point. Okay, so we got 2 points on the graph, and we're going to plot those 2 points. All right, then when you see the derivative at -2 equal to 0, what does that tell you about the point -2, 1 when you have a first derivative equal to 0? Slope is 0. What else might you have? Possible extreme point. Okay, so at -2, 0, that tells us that the point -2, -1 is a possible extreme point. I know this is not on camera. I hope you're writing it down as we go. What you're doing is, oh, it is on camera. Okay, didn't mean for it to be, but it doesn't matter. What we're doing is we're going to get everything in words, and then we'll be able to come back and draw it. Okay, then we have the derivative at positive 2 is equal to 0. Positive 2 equal to 0. So we also know the derivative at 2 is 0, that is also a possible extreme point. So the 0.25 is possible. But we already know for sure, no matter what, we have a horizontal tangent line in there. Okay, now let's go to the next words. The second derivative greater than 0. Second derivative greater than 0 for all x less than 0. When you see second derivative greater than 0, what does that tell you? Concave up. So it's concave up for x less than 0. Second derivative equal to 0 when x is exactly equal to 0. What does that tell you? Second derivative equal to 0. Second derivative equal to 0.
It's a line.
Possible inflection point when x is at 0. So this second derivative 0 equals 0 is a possible inflection point. So wherever x is 0, the derivative is 0, we have a possible, I'm just writing this down, we'll come back, inflection point at x equal to 0. We don't even know what the y value is. We're just doing some sketching here. All right. Then the next little thing says the second derivative is less than 0 whenever x is greater than 0. That second derivative less than 0 tells you concave down for all positive x. So it's going to be second derivative negative. It's going to be concave down when x is greater than 0. Okay, so we've used words to translate everything in the problem, and now we're going to back out and draw the picture. All right, let's see if I can draw it. Okay, it's not going to be a perfect picture. It's just giving us bits and pieces of information. Okay, you're going to get the right shape. You're not going to necessarily know everything just right. Okay, so we're going to plot first the point -2, -1. -2, -1. So we got that point. And we have the point 2, 5. Okay? What? Bad problem. Forget that one. X. 2, 5. Thank you. All right, so we have the point 2, -1 and 2, 5. All right, now the first thing we said is the derivative at -2 is 0, so this point is a possible extreme point. But when you see the first derivative equal to 0, what kind of tangent line am I drawing in there? Horizontal tangent line. So we're going to come down here and put in a little horizontal tangent line. It's a possible extreme point. Okay, and then the derivative at 2 was also 0, so we have a horizontal tangent line. It's a possible extreme point. Possible. We don't know yet. Okay? All right. Now, for all values of x less than 0, so we're in quadrant 2 and 3, it's got to be a concave up kind of problem, and it's got to hit this. Okay. Now, it did not tell me any point, any y value when x is 0, by the way. It just says, let me go to this one. When x is equal to 0, we have a possible inflection point. So we don't know the y value. We got 0, don't know a y value. So they're going to let us just pick wherever we want it to pick. Okay, we're just getting a shape. So I'm going to plot this point first right here. You can put it anywhere you want to because you don't know what it is. They didn't give you enough information. I needed something on the y-axis though, so I can do a concave up. Okay. All right. So for all x less than 0, it's going to be concave up. So how are you going to draw this picture if it's going to go from here to here and it's got to be concave up? Well, all kinds of things we could do. We don't know about increasing and decreasing, but this could be a concave up. If we want to make it an extreme point, we could just switch it around like this. It doesn't have to be that way. it could be like this. You see? Because it didn't tell me about the first derivative. So you got possibilities here as long as it's concave up. All right, then it's concave down whenever x is bigger than 0, and I have to get right here. So one possibility to go from this point to this would be this, if I wanted to make that a max. Or I could do a concave down that just goes like this forever and ever and ever. Okay, as long as it's always concave down. Okay? I didn't know about increasing, decreasing. Is that good, everybody? All right. We're going to have to stop here, I think. Running out of time. Okay, we'll pick up here tomorrow. Be sure to go ahead and look through 2.3 because we're actually going to start curve sketching based on derivatives, where you have to tell where the derivative is positive, negative. Have a great day, everybody.